Okay, thanks first of all for the invitation to be here today. I hope you're all digesting well. And as with the presentation that came before in labor history, I'm welcome the opportunity to talk about less visible actors in space science, steering away from figures such as Elon Musk, who's come up quite a bit today. Although in this case, it's nonetheless a group of white men in South Africa, the systems engineers. So the case focuses on one highly mediatized event, which was the use of astronomy resources in the design of COVID-19 ventilators at the height of the pandemic. It was called the National Ventilator Project in South Africa, and it was widely celebrated as a ray of hope in an otherwise bleak post-colonial landscape. South Africans were hit very hard by COVID-19 because they didn't have the medical resources and infrastructures to treat the number of patients that were coming into the hospitals. And the media portrayed this event as a heroic shift in perspective by the astronomers, from looking at the stars to being humanitarians, to caring about human beings, and even in this article, mistakenly identifying the astronomers as the heroes. But if you dig a bit deeper, a different story emerges, and the protagonists of the story, the heroes of the story, also shift, as well as as I will argue, the ecology of technical action. The South Africa Ventilator Project is in fact embedded in complex relations between South Africa's apartheid history, its public health department, private industry, supply chains, the United States COVID relief program, NASA complex systems, and other sedimented infrastructures of inequality in the Eastern Cape province. So I obviously don't have time to talk about all these dimensions, nor do I know enough about all these dimensions, but I'll just develop one of these factors, which has to do with systems engineering, in particular in how systems thinking established a semiotic link between astronomy and COVID relief, and it really wasn't about astronomers at all. So the overview of my talk is first I'll describe the project. I'll give a brief overview of systems engineering from my rather lay perspective, a conceptual note about how I approach this, and how it kind of encouraged me to think about systems engineering in a slightly more complex way than is often portrayed in the literature. So in April 2020, an engineering team working under the South African Radio Astronomy Observatory, which I'll refer to as SAREO, took over the production of homegrown ventilators in the middle of the COVID pandemic. This work built an alignment between blue sky science and development aims, humanitarian aims. It also reinforced a government narrative, which is a longer history of how high-tech investments can yield innovations. This was several months before the so-called South African variant was making headlines as well, and the media embraced the story as a life-saving turn of events. USAID had already shipped 1,000 conventional ventilators. These kind required they were more complex machines. They required a stable electricity supply and a cement base to install upon, and they also required more invasive procedures, which were not in fact necessary for the majority of cases. And these ventilators actually just sat in a warehouse the whole time. There might still be in this warehouse. It turned out to be an embarrassment for USAID, who then published this report saying they had no control over the process. They didn't have control over the donor countries. They didn't have control over the choice of which devices to send. And they blamed the Trump team of the National Security Council for the lack of control and the lack of prescience in thinking about what made sense in that context. And this kind of failed project stood as a constant reference against which the homegrown ventilator project by the systems engineers was narrated, the SAREO engineers. So in South Africa, the National Ventilator Project's objective was rather to help patients get oxygen by pumping air into their lungs with no need for electricity, because a lot of places didn't have stable electric supplies. They still have a problem stabilizing their electric grid. in some hospitals, especially in Eastern Cape province, there was nowhere to actually install oxygen tanks either, even though they had plenty of oxygen. So in these care settings, there were also few personnel trained to use mechanical ventilators anyway. So the ventilator project had to go back to the planning stages and think about what could actually work in this context. And within 4 months, they designed something, and the systems engineers, and the project closed a year later with 20,000 devices still being used by hospitals. This project was also an opportunity to showcase South Africa's technological feats, the square kilometer array. So these same engineers that were pulled into the ventilator project were actually employees of this, with the mandate to build this observatory, which is now completed, and a second phase is already initiated to expand this observatory to the square kilometer array, which is a much bigger observatory connecting with Australia and other countries in Africa. And it's purported to be the largest scientific infrastructure on Earth by 2028. I don't know if that's true, but that's what they say. Now this project being installed in South Africa, constructed in South Africa, and initially paid for by South African taxpayers. 4 billion rand was this kind of fund that cost to just set up this initial Meerkat, which is kind of a pilot observatory, was highly criticized. It came under critique for being out of touch with African realities. Taxpayers wondered why, when they couldn't stabilize their electric grid, when some areas didn't have clean drinking water, and other problems were still out of reach for so many. Why would they install this extremely high-tech, the most supremely sensitive instrument on the planet, and all of its engineering challenges in a place where they couldn't manage basic things? So I won't go into the details of all that here, but the engineers that it requires are aiming to break a number of records, putting its science heavily on the focus of technical innovation. So when the number of when the COVID pandemic sort of stole everybody's attention away from the SKA, it was an optimal moment to sort of shift the narrative, and Soraya was thought, okay, well, these guys can manage these complex telescopes. They're mechanical engineers, they're electrical engineers. They can be tasked with the manufacture of ventilators. They have the experience that they gained in developing complex systems. So, in fact, it's not a completely random and spontaneous shift in focus. These networks were put in place, the strong engineering skills, in the 1960s, when NASA, in partnership with the Council for Scientific and Industrial Research, so it's the CSIR, it's under the government, built a deep space ground station to help track the Apollo mission and satellites. And this industrial link then was sort of less surprising given the history of South Africa. So during apartheid and isolationism, South Africa undertook and this is a whole other story, which I won't develop, really put a lot of energy into developing its engineering skills due to isolation, partly to continue to establish international collaborations through science rather than through other through politics. And that legacy actually has remained. So the engineering of the dishes itself is also done by South African engineers and manufacturers, and the engineers, the system engineers in particular, the ones who think about how the whole organism works, were the ones that were co-opted into the COVID respirator project, the ventilator project. So I guess what I found interesting, I mean, it's not the first time that mega science derivatives are turned into ordinary technologies. You know, you have the case of the World Wide Web and so on. But I guess what I found interesting was that in some interviews with these guys, I discovered that there was really no technological link whatsoever between the engineering of radio astronomy infrastructures and that of ventilators. So aside from mechanical engineering, radio astronomy, there's no need to think about gas flow. But according to Francois Cap, one of the systems engineers who was in the project, it's really about the details. It's really about thinking about what your goals are, and the details matter. And so for him, it became more apparent that the innovative moment was really in the in the conversations I had across the team. The innovative moment was really in the organizational style of the systems engineers, their ability to solve complex design problems in an efficient way, on time and on a budget. So my interest was to look more closely in the technical skills that allowed these engineers to innovate these particular kind of ventilators in the pandemic. And of course, it was during COVID, so I wasn't able to go there and do participant observation, although that's kind of normally what I like to do as an anthropologist. So most of this was done with online interviews. I did travel to South Africa in 2022 and visited the systems engineers at their Soreo headquarters in Cape Town. And I did examine some of the literature. So for example, I didn't find very much in the sociology of science, but in the history of science, there is this edited volume by Hughes and Hughes on systems engineering. In spite of its kind of importance in the history of military and industrial applications, at least from the contemporary sociology of science, I didn't really find that much. The famous examples include the Battle of Britain during World War II, and we just heard about NASA's Apollo mission. So that was also one of the case studies of this systems engineering approach. And then the textbook on the right is more like an introduction, a really thorough and total holistic guide to the whole practice of systems engineering. NASA's yeah, I took this off of NASA's website, and basically the idea is that the results include system level qualities, properties, characteristics, behavior, function, performance, and the value is to look at the system as a whole, to look at it as a big picture and how the parts are separate from the whole and how they're interconnected when making technical decisions. And in the textbook, and the introduction to that textbook that was on the right, this schema is in it was Hitchens, 2007. It's how systems engineers work and how they imagine schematically and visually. So the left is a figure of an organism, like a cell, I think it is a cell, or a body, and the right figure is a commercial entity, like a company. So again, you have this holistic understanding, and it's visually mapped out. So circles are enclosed, but they're also, as demonstrated by these arrows, they're also open to release pressure. So systems theory, you may know, has been criticized for being sort of removed or disenchanted, too abstract, too symbolic, or what have you from lived experience. So if you take the example of sociologist Nicholas Luhmann, where systems were based on communicative acts extracted from a noisy environment, this approach was criticized heavily for being closed, contained, and reduced in complexity. And for these and other reasons, which I'm not entirely sure about, because I haven't done a huge amount of research on it, systems engineering fell out of popular favor in the 1970s, but even though clearly it's still being used in large complex projects. And just a bit of sort of cultural observation is that the systems engineers seem to have a weird identity in the larger collection of engineers working at Soreo. They had a kind of a stigmatized reputation for being a bit nerdy, geeky, detail obsessed, even a bit of a cult. And they kind of embraced this identity as well. They kind of shyly embraced it. And they expressed, I would say, affective commitment to their approach. So in spite of these criticisms, my observations in hanging out with these guys was that even though a systems approach does emphasize these formal models, these blueprints for action, my sense is that systems engineers don't actually seek to impose their formal model on a situation. Systems engineers may have a professional vision of holism as a format for work, but that they're actually able to code switch quite well. They rather shift perspectives to one of experience as they move along the project. So this map approach, this overview is to enable that and to as a reference point to return to and to anchor the rest of the project. So this brings me to my own conceptual approach, which comes out of totally different background on language and semiotics. So my own attention to the way science mediate between humans and the world. And in my work on space science, I'm looking in South Africa, I'm looking at how astronomers and engineers use technologies to understand the universe. And in my interest has been to find forms of mediation that bring together the universe and earthly imaginaries. So this holistic imaginary is one such formalism, I guess, that seems to mediate across sectors. To take up the language of Charles Goodwin, the professional vision is to map out the whole as an organism, sort of a self-regulating homeostatic entity with some kind of cybernetic feedback mechanism to maintain that stasis. But then it is important to ask, how are these holistic images used in practice? What imaginaries do they evoke, and whose politics do they carry? Do they support the criticisms of systems theories being too macro, too formal, and too out of touch, as is so often claimed? Take an example of such a critique. You have the work of Tim Ingold. Like in the sociology of knowledge, we hear a lot about dualisms, like the formal versus the informal, the tacit versus the formal, or the implicit versus the explicit, and so on. So he draws this comparison between knowledge based in inside the world and experience, and the overview knowledge, the map, whereas figure B is the aerial view achieved by very few except astronauts, and now with satellites and Earthrise imagery, it's become common to imagine the Earth as a whole. But for most, this is a cognitive or digital reconstruction. And he contrasts that with local knowledge, which is obtained by standing in the middle of it, based on practical perceptual engagement. So dwelling in the world, for example. It's easy to see the parallel with systems engineering. So they're clearly, their work is to construct a model like B, but I will suggest that actually in the case of the ventilators, but also in radio astronomy, they seem to toggle between A and B. Oops, what happened? Sorry. Don't know how that happened. Guess I'm gonna have to go a bit faster, huh? So thinking again through the ventilator project, by looking at the language and details of their practice, I kind of identified sort of three phases of thinking, or working, let's say, practices. The first being the planning, indeed the concept design based on the requirements, the contextualization, sort of adjusting to various factors, and then embodying, sort of imagining the system in the sense of a body, and even carrying that in the body. So true enough, in the planning phase, the imaginary, this is actually a design taken from the Radio Astronomy Observatory, the SKA mid top level functions. So they have this signal, it's a map of how the signals are supposed to communicate with each other. And as one of the systems engineers told me, you always have to have a bird's eye view. It's a highly functional model. But then he went on to tell me that when you construct this model, you have to design it with communication. You have to talk with radio astronomy, you have to talk to the scientists. With the COVID case, you have to talk to the doctors, and they will tell you exactly what they want, but then you have to translate that into something that is needed. So you have to figure out how to translate a red Porsche into a transport system that can get you from A to B, because people always say what they want, but actually that's not necessarily what they need. And that's what they call defining requirements. Part of the jargon of systems engineering is to define requirements. Requirements are the bread and butter of systems engineering. So it's a way of reducing complexity and getting to what they think is the functional basis of things. They also are quite good at sifting through the noise. So when the COVID call went out to prevent designs to come in for the ventilators, they had a lot of bids. They had the MIT ventilators, they had the Oxford ventilators, and they had to sort of, with their requirements, they were able to figure out the design that worked best. So even in the planning phase, there is an important element of sifting through the noise, the signal from the noise, of course. But then they're kind of capable of dealing with change. So even though they have their designs and they're highly abstracted, they're able to if they feel like they have control over the whole thing, then they're able to adjust and give it some sense inside an environment. So this includes details of the temperature and the moisture, the technical reproducibility of the design, but also the political environment that was very prominent in their work. South Africa, the political environment was quite present. There were a number of reasons for this, which I won't go into because of time, but this was kind of a background, looming background phenomenon, which they had to adjust for. And the way they described it was that systems engineering was kind of the stabilizing force, which could kind of suffer the throes of the blows of unruly politics. It was their way of accounting for and stabilizing situations that seemed turbulent, as long as you can do it carefully. So that was what was really important. You can manage change carefully, which meant moving slowly. And these are words that they used for how they managed change. And they would position themselves against project managers on the one hand, who are really pushing the schedule, and the astronomers on the other, who are always asking for more. And the engineers were more likely to be more cautious about how much was delivered and to see what was actually needed. So they wouldn't sort of try and cater to the needs or the wants expressed by the astronomers. They expressed this idea of moving along a V form, which is you move down and you move up the V visually in the process of verification up towards validation. So you can see that the starting point is not the same as the end point. It's not just about a hylomorphic form being imposed on a material substrate. It's really starting point and end point are different, and they're accommodating for that shift given all those different contextual factors. And the last category was the kind of the role of the body as an iterative process. So it came in the beginning during the elicitation of the need requirements, and it persisted as a metaphor throughout the process. There was this word embodiment that came up quite a bit, of carrying the wants of the scientists to the manufacturers or through the systems engineers was a process of embodying those needs. There were 3 prototypes that were tested and designed on bodies. In selecting the final prototype that was sent to manufacturing, engineers applied the rigor of testing, following the process meticulously, including everything was checked and double-checked with and on the body. And one of the team tried the prototypes on his body and patients as well. It was really important to inscribe the needs of the body right into the machine itself. So the right balance of air pressure for the context was also inscribed into the CPAP device, continuous positive airway pressure device, which is the one they ended up with. The CPAP device was, I would say, embedded in porous relations with the outside, with the oxygen outside the body, which was in turn nested in an ecosystem of technological and social relations recursively. So this is how system engineers think about technology, interwoven with heterogeneous elements, but if managed carefully, can achieve some kind of homeostasis. It's the secret sauce, according to Peter Roux, CSIR. So just to conclude, sorry for taking a little bit too long, the case points to the value of looking at, again, the invisible labor of space science. It adds to our thinking, I think, about innovative moments and what skills and processes might be involved. Systems engineering, often castigated as a big lumbering beast, proves to be more agile and mutable in context. And systems engineers can toggle between perspectives, and they do so in a very careful manner. This lends to an arguably environmental or even embodied approach to technology or to systems engineering. I didn't spend much time on this today, but elsewhere I argue for the strong national imaginary that enfolds these guys' systems engineering approach in the SKA project. I think this applies as well to the COVID ventilators, because there was definitely a a kind of sense of national pride in how they voiced their work. So I'll stop there, and thanks for your attention.
Thank you very much, Siri, for your presentation. So now it's time for questions. Yeah, Vincent.
Okay, thank you very much, Siri, and it's very nice to hear you once again because it's always fascinating and very, very rich. I have about the same question when I asked Remy about 30 minutes ago. Once again, there is a kind of paradox in the things that you're presenting us. It means that we have all the idea that the space field is dominated by men, white men, highly status level men, and they are in the deep south. And once again, we come to this point that we have people who are graded from Harvard, from Cambridge, from Berlin, Humboldt University, and all these universities, and they are in Los Alamos, in South Africa, in French Guiana, and all these places. And it's a bit of a paradox. And once again, I come to the point that maybe we are missing something with maybe just me. I don't know, maybe I'm just missing something with the space field. It is that it is also a territorial matter. It's also a territorial matter, which is highly beneficial to the South. And when I mean the South, it's not only the deep South like South Africa or Chile or these places, but it can be French Guiana in Guyana. It can be, of course, Scotland. Scotland is not the South, but it's something like this. And so I just wanted to know what you think of this kind of paradox that we have highly graded people, white men and so on, and they are in places which are in the middle of nowhere, and what it means, this kind of paradox, which is a bit striking for me.
Thank you. Yes, I think that it's easy to think of them as being in the middle of nowhere, but I think they're actually mostly in Cape Town. The observatory is an 8-hour drive into the Karoo in the desert. But I guess if you mean the global South, yes. One thing is that the decision makers to install the radio observatory in this spot were not the engineers who work on it. So I guess in the same case as the last presentation, the people who labor on the machine are not those who decide to put the machine there in the first place. And so there's obviously this global north-south relation going on. The people who, I mean, it was the South African government who bid to do it, but the funders and most of the, I mean, aside from this initial project, most of the whole planning and organization of the entire thing comes from the global north, the consortium of countries in the north, and China. So, so the people who end up, if we're talking about labor, as we are in this panel, then I guess then there's some kind of parallel there, that the figures, the protagonists, the heroes of the story are not coming from these places, and it's the workers, the ones who are doing, you know, the tedious stuff, the visible work, that are being told in these stories. So that's one thing. The other thing, of course, is the physical value of to some extent, of putting a radio observatory in certain places of the world, so-called places where there's little radio frequency interference and so on, and relatively dark skies. So there are a bunch of dynamics. I think they're kind of embedded and refract on each other, which make it so. And I guess it's these paradoxes that we're supposed to pull out and make the topics of our stories.
Thank you. Yeah. Another question?
Yeah, thanks so much for this talk. This is, I don't know if you can see us well, but this is.
No, I can see one head.
Okay. This is the person who just gave the last talk. Yeah, this is a really great paper. So I've also looked into sort of the history, not the present, of systems engineering in NASA. And one of the things I saw a lot is it was a very controversial movement within the, you know, on one hand, this was really popularized by the Apollo program, where it had been really kind of central to the design philosophy and whatnot. And then, you know, sort of famously, NASA tries to sell systems engineering as a sort of, we've had the proof of concept and now we're going to do it in all these other places. We're going to redesign the cities and we're going to be like spaceships and blah, 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 blah. And we know how to run a water system. We know how to run a municipal government because we've done it like this. And they pretty immediately hit pushback, including from people within NASA who would say, you know, okay, it's great that you're trying to incorporate some idea of the social or something or culture and into, you know, engineering philosophies and design philosophies. That's interesting. But at the end of the day, you're an engineer. What do you know about this kind of stuff, right? So there was a very philosophical push against this kind of methodology, that this was an inherent overstep. And then my sense, I really don't know that much about the timeline past like the 1970s, is that it really declines within the agency. And then it only survived in like a few kind of laboratories that really see themselves as still doing, you know, we're systems engineers, blah, 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 and no longer this sort of agency-wide thing. But maybe that's totally my misperception. So yeah, what do you think of that? And what's the sort of pushback, the criticisms of systems engineering, either from other people or from within these kind of communities?
Yeah, I don't know. That's a question which I haven't fully explored inside, beyond this, so much beyond this case study, other than how they're perceived in the larger Soreo organization. But I think they're held in extremely high esteem, and in fact, they are the fundamental organizers of the entire. You know, as I tried to emphasize, like the whole beast. I mean, the whole thing is really based on their planning. So I think it's completely fundamental. It's not an add-on. It's not marginal. It's basic to everything. And as far as I understand, some of them even have been traveling to North America as well to exchange ideas and technologies. So they're building this new generation radio observatory in New Mexico, which is going to be also based in, I think, systems engineering planning. So I think that they're not an isolated case. But yeah, I don't know. It's a question. I read again and again that it fell out of favor, but if it's still in extremely present in these large scale projects, I guess that has to be qualified somehow. And that's actually research I haven't done. So I'd be glad if you had any literature to throw on that topic to share. So I can't really answer your question properly, but it's a question.
Thank you very much, Siri. More questions? Yeah, one more.
One more still, Vincent. Thank you very much, Siri, once again. I was very interested by your quotation that the end user was wrong about his needs, but he thought that he needed a Porsche.
Yeah.
But actually, it just needed to go from A to B. Is it something? Is it linked to the conflict or the difficult relation between the scientists and the engineers, or is it something very different which is underlying this quotation?
Well, what else? I mean, I think it has to do with how these engineers work in general. So it has to do with their relations with the scientists and the relations with their politicians, which they see as somewhat antagonistic because they don't work as idealists. They think of themselves as very praxeological, very pragmatic. So they insist on their capacity to translate wants into needs. And I think also they're much more grounded in you know, economic, political realities on the ground. So they have to think about what they can actually do, not what they imagine. What like scientists, for example, might not be in South Africa. They'll be somebody else, somewhere else. But they'll think, oh yeah, that'd be good to have that extra this and that. I'm not sure if that's what your question was, or if you had something else in mind when you said if it was something about something else. What is that something else? I don't know.
I think it answered. Thank you very much, Siri. We have one last question that is online. I think you can see it as well, but I will read it for you. Are you familiar with the development of the private spaceport Overbeck, at the Denel Overbeck test range? If so, what do you think are the apartheid legacies, and what is the reception from the public?
No, I don't know. I don't know about this spaceport at Overberg. So I guess I can't respond to this question. I can respond in respect to the SKA, but not with the Overberg.